Thank you, sir. So my presentation is on spin-induced band gap opening in strained graphene. And my slides are divided in an outline. Like first, we'll be having a brief introduction on the wonderful and amazing properties of graphene. Then the already available techniques that are used to open band gap in graphene. And then there are certain drawbacks that they face. And then these techniques and the material properties of graphene, they suggest an entanglement and interplay between strain and spin. Strain and spin actually, that's an excellent duo for various for exploiting the material properties of graphene, enhancing them or tuning them. So in context to that, we'll be dealing with the magnetic properties of graphene, and then the exotic spin engineering and idea for band gap opening in graphene, and finally we'll come up with spintronics as a solution. So since in 2010, the groundbreaking experiments regarding the two-dimensional material graphene has faced the Nobel Prize in physics. There has been no looking back. The laws of condensed matter physics that come into play in these mysterious 2D material graphene are intriguing in themselves. Atop of that, graphene offers a whole lot of technological pros due to its amazing electronic, optoelectronic, thermal, and mechanical properties. As for the electronic properties, graphene has massless fermions. That is, the energy bands near the Dirac point exhibit linear dispersion relation. Quantum Hall effect is observed at room temperature. It exhibits very high mobility of the order of 10 to the power 4 to 1.4 into 10 to the power 5 centimeters square per volt second, and under particular enhancements up to 2.5 into 10 to the power 5 centimeters square per volt second. Moreover, field tunable carrier density with very low resistance that makes it very suitable for using PET devices. And it has the potential of replacing copper in microelectronics technology in most interconnects, etc., because reportedly it can sustain million times higher carrier current density as compared to copper. Graphene composites have very high electrical conductivity, and therefore they are used for lithium-ion batteries, for bioelectronic sensing devices, etc. Chemically derived versions of graphene are available, and they have exceptionally high energy density and are used in alpha capacitors. The optoelectronic properties of graphene are also very attractive. Like graphene sheets are used for transparent electrodes. Their flexibility and their mechanical strength coupled together enable them to replace indium tin oxide glass materials these days, because single layer graphene offers a transparency of up to 97.7%, almost close to 98%, that is, only 2% absorption. Thermal properties of graphene. Now this is pretty interesting. The thermal properties of graphene, they are enhanced good features, but they offer a twisted strain and symmetry dependence. Like the normal thermal conductivity of single layer graphene is 5 into 10 to the power 3 watt per meter Kelvin. However, for helical or tube-like graphene structures under torsion, the conductivity is completely different. And so is it for the corrugated sheets under uniaxial compression. Therefore, this shows that there is an interesting interplay between the material properties of graphene and their strain dependence. And this hints that the material properties of graphene may well be varied or tuned using straintronics. Mechanical properties of graphene also support this. Graphene is the hardest or the strongest 2D material known till date. And it has a Young's modulus of the order of 1.1 TPa. So that makes it, and it has a reversible elastic limit of tensile strength, which is very high and it's greater than 20%. Therefore, this makes it a suitable material for straintronics. But in spite of having so many advantages, graphene has this obvious disadvantage that it is a gapless material. So to overcome this, till now we have seen various kinds of technologies like substrate-induced band gap opening, and there are experimental reports and theoretical studies. In this kind of band gap engineering techniques, we actually use a substrate. On the substrate, graphene layer is either it's grown epitaxially or it's grown somewhere else and then transferred. Layer transfer is also a common process in graphene. It can be single layer, bilayer, or monolayer. But depending on the substrate on which the graphene layer is there when the device is being formed, graphene exhibits a particular band gap. Like on hexagonal boron nitride, which is again on nickel, and on the 111 phase, there is a band gap of 0.5 electron volt. By scanning tunneling spectroscopy, we have observed these observations are there. Then graphene, but theoretical studies say graphene on hexagonal boron nitride offer a band gap of 0.053 electron volt, whereas the band gap is almost zero if graphene is on copper. For silicon dioxide substrate, graphene offers a band gap of 0.52 electron volt, which is higher than that hexagonal boron nitride nickel combination, if only it is terminated with oxygen. If it is terminated with hydroxyl, then no band gap appears. But the principal disadvantage is that this epitaxial graphene band gap is not tunable. Depending on the substrate, it's not tunable. And the Fermi level lies inside the conduction band for doped graphene, though it's easy to grow silicon carbide. Then the techniques used to open band gap in graphene also include substitution, chemical substitution, or doping. Two types of dopants have been used, like nitrogen dopant and boron dopant. And for nitrogen dopant with a methane plus ammonia precursor, 8.9% of doping concentration has been available. DC arc discharge plus graphite electrodes in ammonia atmosphere yield a nitrogen content of 1% by weight. And electron energy loss spectroscopy XPS observations, they report 1% nitrogen concentration in pyridine plus hydrogen atmosphere, whereas for boron doping, 1 to 3% concentration has been achieved. Now, theoretical studies, these are the experimental reports that this percent of dopant may be induced into graphene. And theoretical studies say that both nitrogen and boron dopants energetically prefer H sites. And this is particularly evident for graphene nanoribbons. Boron doping as high as 4% does not even alter the band structure of graphene, let alone these are DFT first principle calculations, let alone giving rise to a band gap. Minimum quantum interference and increased localization sensitivity may be the reason for this. Remarkably, boron assists in graphene nanoribbons to filter their spin. Therefore, this boron doping interferes with the spin state of graphene. But band gap opening is a bit challenging with using these dopant ideas. To achieve uniform doping throughout the graphene sheet is challenging, and therefore, as we have already pointed out, near the H sites, it is something varies. The band structure varies. So this is it faces difficulties. And substitution doped graphene has much lesser conductivity and carrier mobility as compared to pure graphene, which basically defeats the entire purpose of graphene electronics. Then we may also use graphene hybrids, like we can use simultaneous boron and nitrogen doping in graphene, resulting in some BCN hybrid nanotubes or semiconductors. For graphene on HBN hybrids, we find energetically favorable states, and opening of band gap has been predicted for such energetically stable nitrogen terminated boron nitride structures. HBN zigzag graphene nanoribbons are there on HBN. They exhibit half metallic dispersion, half metallic. And experimental reports say that fabrication has resulted in BCN films of poor crystal quality. And CVD grown graphene or HBN hybrids on copper substrates exhibit dual optical band gap of small width. So drawback, band gap opening depends heavily on domain size, but precise control of domain shape and size remains challenging. Now we have options such as graphene nanoribbons, patterned graphene, and graphene origami, which is a subset of patterned graphene. But for graphene nanoribbons, the band gap opens, or they are expected to open by DFT calculations due to quantum confinement. And it is only possible for diameters below 10 nanometers, diameters, not radius. And the fabrication challenges remain for such small dimensions. And then patterned graphene, the periodic patterning of graphene with nanoscale defects passivation, doping, perforation appears to open up band gap. However, what kind of periodicity will open up what magnitude of band gap or what nature of band gap, that is not quite evident. It remains a mystery. Graphene origami is also a subset, and it's periodically folded graphene films, which we call denote by graphene origami, and the curvature effects result in spin polarized current. So again, we find that structural formation of graphene alters the spin state of graphene. Therefore, like the electromechanical properties of graphene, which depend heavily on the strain and symmetry of graphene, its magnetic or spin state also depends on the graphene structure or on the strain state of graphene. The general drawback of all these techniques that have been proposed and about to be implemented till now is that their carrier mobility decreases highly due to this whatever substrate or origami or patterning or folding pattern that has been used. Now, from all these experimental and theoretical studies, it is very evident that from first principle calculations mainly, it has been found out that electronic properties of graphene depend on strain, and strain state of graphene depends on the magnetic state of graphene. We find that symmetric strain has as such no effect on the band structure of graphene. It still continues to be zero gap, whereas asymmetric strain opens up a band gap in graphene. This may be attributed to the anisotropic Poisson's ratio of graphene. That is, this Poisson's ratio of graphene is it has a tensor form and it's different in different directions, and 0.1732 it remains constant under small applied strain. Now, if the strain is applied in a direction perpendicular to the carbon-carbon bonds, then a band gap of 0.17 electron volt opens up at the Fermi level, but the magnitude of the strain has to be 7.3%. And for a strain of 12.2% parallel to the carbon-carbon bonds, a band gap of only 0.486 electron volt opens up. So we find that there is an interplay between strain and spin in graphene. The symmetric biaxial or uniaxial strain of the either it's symmetric biaxial, that is it has the same magnitude along both the axes of a plane. Since graphene is, we are considering graphene a 2D material, so along both the two of the axes the magnitude of the strain is the same. It's symmetric biaxial, or if it is uniaxial, then the magnitude of the strain may be as high as 20%, but that would not yield any band gap. Graphene would still be a zero gap material. However, for compressive or tensile shear strain, that is a bit shear strain, so we may consider it to be a bit asymmetric of the order of 20%, only 0.4 electron volt of band gap may open up. Asymmetric biaxial strain leads to band gap opening. Minus 20% of compressive strain in armchair direction and 11% of tensile strain in zigzag direction reportedly opens the band gap of 1 electron volt. However, the magnitudes of the strain are very large, and experiments show that despite being under a strain state as predicted by the DFT calculations, the expected amount of band gap do not open up in graphene. For armchair graphene nanoribbons, a tensile strain in the armchair direction is applied, then a ferromagnetic to non-magnetic transition occurs. And 11% for monolayer, 3% for bilayer, and 2% for trilayer. This is the amount of strain necessary for this ferromagnetic to non-magnetic conversion. However, spin polarization in armchair edges decreases, spin splitting at the Fermi level itself decreases, and in further increase in strain results in decrease in spin moment. Therefore, the magnetic properties of graphene show significant dependence on strain. From this, we may say that strain and spin, these two intertwined factors in graphene which interfere with each other's states, may be used in conjunction to open up a band gap in graphene. And from experimental study, using scanning tunneling microscopes or molecular dynamics under only LAMPS configuration has shown that strain engineering of graphene nanostructures results in charging effects and pseudomagnetic fields in monolayers. And also, starting from bilayer up to multilayer graphene, graphene executes a parabolic band structure under particular strain states. And graphene is particularly suitable for spin engineering as well because it offers the longest room temperature spin relaxation length, weak spin orbit coupling, long spin diffusion length, even in bilayer graphene, which ranges only to several micrometers. And these are the properties of graphene, strain properties or spin properties of graphene as compared to various popular semiconductors. The semiconductor metals are shown in green like gallium arsenide, germanium, and silicon, and certain metals like silver, aluminium, copper. So we can find that graphene properties are the best. So an exotic spin engineering idea has been proposed to open the band gap in graphene, and that can be low temperature experiments show that topologically non-trivial state exists in graphene at low temperature. And the conduction band minimum and hole band maximum, though at different points in the k space k and k dash, that is, it's not a direct band gap, also are connected only near the sample edges. That means inside the material, deep inside the material, spin polarized bonds open up. So the magnetic field has been applied. Once the magnetic field has been applied to the sample, then all possible sources of spin orbit coupling from external sources have been disabled or minimized. Then it has been observed that transitions of resonant microwave excitations occur, and as a result of that, coupling of charge carriers having opposite spins occur. So from these DFT calculations may reach the conclusion that the resistance in graphene is proportional to the applied microwave excitation frequency. So under no applied magnetic field, the transitions are completely blocked. And once a magnetic field has been applied, the strain states may be in such transition order that the band gap of up to the order of 42.2 into 10 to the power minus 6 electron volts may open up. This experiment supports that spin orbit coupling in graphene leads to band gap opening. And therefore, if we select a graphene substrate which opens up a certain amount of band gap or is on the verge of opening band gap for graphene, and then we apply a considerable magnetic field, then a band gap may open up in graphene without having the necessity of being applied a very high magnitude of strain, and therefore
Okay.